Hey everyone, and welcome back. Have you ever really stopped to think about the absolute magic that happens every time you click a link? Well, today, we're pulling back the curtain on computer networking. This is the invisible engine that runs our entire digital world. All right, let's dive in and figure out the rules of the road for the internet.
Seriously, think about it for a second. You click on something, and almost instantly, a web page, a video, an email just appears. It feels like it has to be magic, right? But it's not. It's actually one of the most sophisticated, beautifully coordinated systems humanity has ever built. So how does it really work?
You know, the best way to picture it is like this: a massive, global digital superhighway. And just like a real highway system, it is not chaos, not at all. It has lanes, on-ramps, traffic cops, and a very, very specific set of rules that every single vehicle, or in our case, every little piece of your data, has to follow to get where it's going.
Okay, so to navigate this whole superhighway, we're going to need a map. Here's our game plan. First, we'll follow a single click on its amazing journey. Then, we'll look at the internet's core blueprint, meet the actual physical hardware that makes it all run, and see exactly how your data travels. After that, we'll learn the language that all these devices speak. And finally, we'll take a quick trip back in time to see how this whole thing even got started.
So how on earth do you manage something as mind-bogglingly complex as the entire internet? Well, you do what any good engineer does. You break it down into smaller, manageable pieces. The solution is a layered architecture, something we call a protocol stack. I want you to think of it like a super efficient postal service, where each department has exactly one job to do before it passes the mail along to the very next department.
And this is it. This is the TCP/IP model. You could call it the 5-layer cake of the internet. At the very top, you've got the application layer. That's what you actually see and interact with, like your web browser. All the way down at the bottom is the physical layer, the literal wires, the cables, the radio waves. Now here's the absolutely crucial part. Each layer only talks to the one directly above it or directly below it. This division of labor is the secret sauce. It's what makes the entire system work without just collapsing into total chaos.
Now, this layered blueprint isn't just some abstract idea. It's brought to life by actual physical hardware. So let's meet the key players, the traffic controllers and the road workers on our digital highway.
Okay, what's really cool here is seeing how each piece of gear maps to a specific layer. I mean, first things first, your computer needs a way to plug into the network, right? That's your NIC, the network interface card. Then you have a hub. It's kind of dumb, honestly. It operates at the physical layer and just shouts any information it gets to every single device connected to it. A bridge is a little smarter. It's a local traffic cop that knows which computers are on which side of it, so it doesn't forward unnecessary traffic. And then you have the router. This is the master navigator, working at the network layer. It's the genius that reads the long-distance address on your data and figures out the best possible path for it to take across the entire internet.
So we have the layers, and we have the hardware. But how does your actual data, say a request for a web page, get all packaged up and sent on its way? Well, it's this fascinating process called encapsulation.
Imagine you're sending a letter. Your data, the photo you're uploading, is the letter itself. As it travels down through those layers we talked about, each layer puts it into a new, bigger envelope with new instructions. The transport layer adds an envelope with the port number, which is like a specific department in an office building. Then, the network layer adds an even bigger envelope with the IP address, the actual street address of the building. And finally, the data link layer adds one last wrapper for just the very next stop on the journey. It's a brilliant system for getting information ready for travel.
Now, once it's all packaged up, how does it actually travel? Well, early networks use something called circuit switching. Think of an old-school telephone call where a dedicated, private line is opened up just for you in your conversation. But the internet uses packet switching. Your message gets chopped up into tiny little pieces called packets, and each one is sent out to find its own best path through the network, almost like a fleet of delivery bikes weaving through city traffic. It's way, way more efficient, and it means the whole network can survive even as some roads are totally blocked.
So for all these millions of different devices and networks across the entire globe to understand each other, they all have to speak the same language. In networking, these languages are called protocols. Let's take a look at the most important ones that decide how our data is addressed and transported.
Okay, so here's a crucial piece of the puzzle. It's not enough to get data to the right computer, you have to get it to the right application on that computer. How does that happen? With a socket address. It basically combines the computer's IP address, its street address, with a specific port number, the apartment number. This is the secret sauce. It's how your computer can be browsing the web, receiving email, and video chatting all at the exact same time without getting all the messages mixed up.
So, at the transport layer, your apps get to choose between two main delivery services. On one hand, you've got TCP. This is the reliable one. Think of it like registered mail. It checks and double-checks to make sure every single packet arrives and that they're all in the right order. You wouldn't want an email with half the words missing, right? That's why email uses TCP. On the other hand, you have UDP, the fast one. It's more like sending a postcard. You just toss it in the mail and hope for the best. It's perfect for things like video streaming or online gaming. If one tiny packet gets lost, you might see a split-second glitch on your video call, but for that, speed is way more important than perfect 100% accuracy. But listen, these rules and protocols we depend on every single second didn't just appear out of thin air. No way. They are the result of decades and decades of incredible innovation. So let's take a quick look back at how this digital superhighway was first paved and how it grew from a tiny government experiment into the global network we literally can't live without.
It's kind of wild to think that it all started way back in 1969 with something called ARPANET, which connected just 4 computers. That's it. The huge turning point was in 1982 when TCP/IP was established. That became the universal language, the Rosetta Stone that allowed all these different isolated networks to finally talk to each other. After that, things just took off. In 1990, we got Archie, the very first search engine. And then the game truly changed forever in 1993 with Mosaic, the first popular graphical web browser that made the internet accessible and easy for everyone to use. And that brings us to today. We've journeyed from a single click all the way down through the layers, across the physical hardware, and back through time. The foundational architecture we've just talked about is incredibly resilient. It's amazing. But here's the kicker. It was designed over half a century ago. It really makes you wonder, doesn't it? As we connect billions more devices and demand ever-increasing speed and security, what will the internet's rules of the road look like in the next 50 years?